Hello all. In my previous lecture, I discussed one of the classification of the material, that is semiconductor, and the various types of semiconductors like direct bandgap semiconductor and indirect bandgap semiconductor. Okay, and one more concept I discussed, that is why silicon is preferred in fabrication than germanium. Now in this lecture, I will start with another classification of the material, that is conductor. Right. First of all, what is a conductor? So conductor means the material whose energy gap is approximately zero. Such a material is called as what? Actually conductor. Okay. So in this, electrons are moving from valency band to conduction band without need of any external energy. Means we need not apply any external energy to move from electron valency band to conduction band, because both conduction band and valency band both are overlapped. Right. And what are the example for the conductors actually here? The example for the conductors are silver, copper, gold, aluminium, etc. These are the few examples of conductors. Okay. Simply we can say all metals are, we can say conductors, but all conductors are not metals. Right. Here, among all those metals actually, which one is the best conductor? Actually, silver is the best conductor, because it offers high mobility compared to copper and aluminium and gold. Okay. So where we use this silver? Actually, this silver can be used in electrical wiring in ICs, integrated circuits. Okay. So where we use the copper actually here? The copper can be used as electrical wiring in electrical circuits. Right. And where we use this gold actually? This gold can be used as a reagent. That means when we add the gold to the semiconductor material, then it improves the speed of the device. Okay. So when we add a gold to the semiconductor material, so it increases the recombination centers, thereby the conductivity is improves. And finally, where we use this aluminum, actually this aluminum can be used as a metal contacts in integrated circuit in olden days, but nowadays actually we are using copper, because the copper offers better conductivity than aluminum. Right. These are the few examples of conductors. Copy the energy band diagram and examples. Yeah. Write down points. The material whose energy gap is zero. Whose energy gap is zero. Such a material acts as a conductor. Right. In this, electrons are moving from valency band to conduction band. Electrons are moving from valency band to conduction band without need of external energy. Without need of external energy. Because both conduction band and valency band are overlapped. Conduction band and valency band are overlapped. Right. Now write down the examples. Yeah. Note. Silver is the best conductor among all those conductors. Because it offers high mobility. Right. And the next topic, current flow in a conductor. Yeah. Next, see, to explain the current flow in a conductor, actually, here I am considering a sodium sheet. I am considering a sodium sheet. In this, the sodium atoms are uniformly arranged, and also each sodium atom has one valence electron. This one valence electron is responsible for the current flow in a conductor. Right? Next, this one valence electron is donated to the nearby atom. Then this sodium atom becomes sodium ion, and the valence electron become the free electron. Right? You know, these free electrons are uniformly distributed in a sodium sheet, and also it having a random motion. It having a random motion. Due to this random motion of free electrons, actually, what is the net current in a conductor? Zero. The net current equal to zero. Then what we will do, actually, then we can apply some external electric field. Right? Due to this applied external electric field, what happens? Okay, these electrons are moving in a particular direction. Previously, without applying an external electric field, actually the electrons are moving in a random motion. After applying some external electric field, actually these electrons are moving in particular direction. That means it can move from the low potential to high potential, and it can produce a current from a high potential to low potential. That current is called as what? Actually, free electron current. Right? And one more important point, actually. So why electrons are moving in a random motion or in zigzag path, actually? Due to collisions. See, due to collisions, at each collision my electron changes direction. So that's why electrons are travel in random motion or in zigzag path. Okay. Now write down important points. Consider a conductor, in bracket, nothing but sodium sheet. Consider a conductor, in bracket, sodium sheet, and it is uniformly distributed. And it is uniformly distributed. Next. And each sodium atom has one valence electron, and each sodium atom has one valence electron. This one valence electron is responsible for current flow. And also it donated to the nearby atom. Then sodium atom becomes sodium ion, and valence electron become free electron. Valency electron become free electron. Yeah, please underline free electron. Yeah, next point. These free electrons are uniformly distributed. In a sodium sheet. And having a random motion. Due to thermal energy. Right. Next point. Due to random motion of free electrons, the net current becomes zero. Yeah, underline net current becomes zero. Next point. When an external electric field is applied, then electrons are moving from low potential to high potential. Electrons are moving from low potential to high potential and produce a current from high potential to low potential. That current is called as free electron current. In bracket IN. Free electron current in bracket IN. Yeah. Underline free electron current. Note. Electrons can travel in zigzag path or random motion because of collisions. Next, at each collision, electron changes direction. Yeah. Copy this diagram. Right. And next topic, mean time. And it is denoted with 1000. Yeah, what is mean time actually? Mean time is nothing but it is the average time taken by an electron between two collisions is called as mean time. Yeah, mathematically the mean time is nothing but journey of an electron by number of collisions is called as what actually? Mean time. Yeah, and one more definition actually, mean distance. It is denoted with L. What is mean distance actually? Mean distance is nothing but it is the distance traveled by an electron between two collisions. It's called as what actually? Mean distance. Mathematically, what is mean distance actually? Distance traveled by an electron. Distance traveled by an electron by number of collisions. Is called as what actually? Mean distance. Right? Yeah, completed. And next topic, drift velocity. It is denoted with VD. So what is drift velocity actually? The drift velocity is nothing but the velocity of speed which acquire between two collisions is called as drift velocity, or the speed or velocity due to applied external electric field is called as what actually? Drift velocity. You know, drift velocity is computed by using law of momentum. What it is? Law of momentum. What is law of momentum actually? Law of momentum is nothing but momentum applied. Momentum applied is equal to momentum gained. What is momentum applied actually here? What we are doing, we are applying some external electric field to a conductor or a semiconductor. What happened actually? The charge carriers are flowing, right? That means momentum applied is nothing but force into time. What is momentum gained actually? If you are applying some force, nothing but external electric field, the electrons are moving, right? So it gains a momentum, that is mass into velocity, right? Here what type of force we are applying? Actually electrical force, that is minus E into capital E into tau C is equal to Mn into Vd. Now what is Vd here? Actually Vd is nothing but E tau C by Mn into E, right? Let I can define mu n. What is mu here? Actually E tau C by Mn. Now what is drift velocity here? The drift velocity is nothing but Vd equal to minus mu into E. This is the equation of the drift velocity due to applied external electric field. Okay. Here this negative sign indicates what? Actually the direction of the velocity is oppositely to the external electric field, applied external electric field, right? Right on. Put the heading drift velocity. Yeah. The speed or velocity which acquire between two collisions. Is called as drift velocity. Next point. Drift velocity is computed by using law of momentum. Yeah, underline law of momentum. That is momentum applied. Write down like this. Momentum applied is equal to momentum gained. And copy the derivation. Yeah. The negative sign indicates, write down, the negative sign indicates the direction of the velocity is oppositely to the applied external electric field. Next heading, mobility. Yeah, what is mobility actually? Mobility is nothing but it is a measure. Of how freely a charge carrier can travel is called as what? Actually mobility. Or we can also express like this. Means we can also define like this mobility. Actually mobility is nothing but it is a ratio of drift velocity per unit electric field is called as what? Actually mobility. Drift velocity per unit electric field also called as what? Actually mobility. Okay. Now I can define the units of mobility actually. What is the units of mobility? Tell me what are the units of velocity actually? Velocity of units is meter per second, right? Distance per unit time. And what is the units of electric field actually? Volt per unit distance, nothing but volt per meter, right? Now what are the units actually? Meter square per volt second. In series system this is centimeter square per volt second. Very important computer bit, right? And next here this mobility depends on what actually here? So what is the expression of mobility actually? Mu equal to E tau C by Mn. Here charge of the electron is constant and mass of the electron also constant, means that means mobility will depends on what actually? The mobility will depends on mean time. This is also important relation between mobility and mean time, right? Copy. Write in your notes. It is a measure of how freely a charge carrier can travel. Or it is the drift velocity per unit electric field. That is, I don't mu equal to Vd by E, and copy. Yeah. Completed? Next, write down an example in your classroom workup, that is question number 1. Question number 1. Write down an electric field of 10 volts per centimeter, 10 volts per centimeter moves an electron a distance of 2 centimeter in 1 microsecond. Mobility of an electron is right. Now all of you read one question. All of you read the question once actually. What is given that actually they given an electric field, right? Question number 1. They given an electric field actually how much? 10 volt per centimeter. Also they given a distance. How much it is? 2 centimeter. Also they given a time. How much it is? 1 microsecond. What we want to calculate actually? Mobility, that is mu, right? So first of all, what is the relation between mobility and electric field actually? We have a relation, that is drift velocity is equal to mu into E. Here neglect minus sign actually. Here this minus indicates the direction. Consider only magnitude. Okay. Here we know electric field, but we don't know drift velocity. But they given actually time and distance, right? What is the relation between velocity and distance actually here? So we know velocity is nothing but distance by time. So what is the distance here actually? 2 centimeter, and the time is nothing but 1 microsecond. Now what is the velocity here actually? 2 into 10 power 6 centimeter per second. Yeah, this is the velocity, right? Now what is the mobility here actually? Mobility is nothing but okay, Vd by E. So what is the velocity here actually? 2 into 10 power 6 by 10. Now how much it is actually? 2 into 10 power 5 units centimeter square per volt second. The mobility of electron is 2 into 10 power 5 centimeter square per volt second. Copy. Example. In your classroom workbook, question number 2. Question number 2. Write down a question. In a metal, electron has a mobility of 1000 meter square per volt second. 1000 meter square per volt second, and Mn equal to 0.25 m naught. 0.25 m naught. And velocity of an electron is 10 power 7 meter per second. Find mean time and mean distance. Find mean time and mean distance. Right. I'll read the question once. What is the given data actually here? So in a metal, electron has a mobility. How much? 1000 meter square per volt second. Yeah. Also they given Mn equal to 0.25 m naught. Actually, what is Mn? Mn is nothing but effective mass of an electron, right? And m naught is nothing but what actually? Actual mass or true mass of an electron, right? Here, what is the difference between effective mass and actual mass actually? This effective mass is calculated under force condition, and actual mass is calculated under no force condition or free space condition, right? What happen if you apply some external electric field? Okay, what happened? The charge carriers are moving. That means the mass of the electron also be changed. Mass of the electron also be changed. For example, see here, for example, I am standing here. What is my actual weight actually? Let us say 84, right? This is my actual weight, right? Okay. and now I am walking. Now I am walking, right? Then what about my weight? Actually, it's still 84 and it will change. Yeah, surely it will change because of applied force. The same way, so when you apply an action electric field to a conductor or a semiconductor, actually, the charge carriers are moving, their mass also be changes. That mass is called as what? Actually, effective mass. Okay, if you are not applied any force, okay, then there is a mass actually that is called as the actual mass of an electron. That is the difference between effective mass and actual mass. And one more parameter they given, actually the drift velocity, that is 10 power 7 meter per second. Yeah. What we want to calculate actually here? We want to calculate mean time and the mean distance. Right. Now tell me, what is the relation between mobility and mean time actually here? We know mobility equal to E tau c by Mn, right? So from this, tau c equal to mu n into Mn by E. What is the mobility here actually? Mobility is nothing but 1000, Mn is nothing but 0.25 m naught. E is nothing but charge of electron, that is 1.6 into 10 power minus 19. Now 10 power 3 into 0.25 m naught. M naught is nothing but mass of an electron, that is 9.1 into 10 power minus 31, 1.6 by 1.6 into 10 power minus 19. Now what is the answer here actually? The answer is 1.42 nanosecond. This is about mean time, right? Now how to calculate a mean distance? So we know what is the relation between velocity and mean distance actually. Velocity is equal to distance by time. Now L equal to velocity into time. So velocity is nothing but 10 power 7 into 1.42 into nano means 10 power minus 9. Now 1.42 into 10 power minus 2 meter. This is about mean distance, right? Copy? Yeah. Next. Next topic. Effect of electric field on drift velocity. This is also important concept. Effect of electric field on drift velocity. Right. See, when we apply the extra electric field to a conductor or a semiconductor, so what happens? The charge carriers are flowing, right? Right. Charge carriers are flowing. Flowing means it having some velocity, right? How it will affect it? Due to applied external electric field. See here, first of all, now what is the relation between velocity and applied external electric field? Actually, Vd equal to minus mu into E. Just we derived, right? This is the relation between drift velocity and applied external electric field. You know, this applied external electric field can be classified into three ranges actually. The first one is small applied electric field. The range is electric field is less than 10 power 3 volt per centimeter. Next one, medium applied electric field. The range is E value lies between 10 power 3 and 10 power 4 volt per centimeter. And the last one, high applied electric field. E greater than 10 power 4 volt per centimeter. Means when we apply the different value of an electric field, what happened to the velocity? That we want to check actually, right? The first case, what is the first case actually? For small applied electric field. Small applied electric field. See, for small applied electric field, actually what happened, the drift velocity is linearly increases. Linearly increases with applied electric field. See here, this is the relation between drift velocity and applied electric field, what actually linear, right? So when you apply the small applied electric field, now the drift velocity is linearly increases with applied electric field. Linearly means VD is directly proportional to E. That means what about the mu actually here? The mu is constant. Mu equal to constant, right? Mobility is constant. And the second case, that is if you apply the medium applied electric field, means the value lies between 10 power 3 and 10 power 4. What happened? The drift velocity is sublinearly increases. Sublinearly increases with applied electric field. Sublinearly increases means that is VD is proportional to under root of E. Here, if you apply the small applied electric field, it is linearly increases. If you apply the medium applied electric field, it is sublinearly increases. Why? Why? Because, right? See, because as electric field is increases, what happen? The drift velocity is increases, right? If the drift velocity increases means what about the chance of collisions actually? The chance of collisions also be increases, right? If chance of collisions is increases, what happen? If chance of collisions is increases actually, what about the mean time actually here? The mean time is decreases. If the mean time is decreases means what about the mobility here actually decreases. If mobility decreases means again what will be the drift velocity here actually decreases, right? See here, see all of you here. If the drift electric field increases, velocity is increases. But at the end actually what happens, the drift velocity is decreases because of what actually collisions. That's why here the drift velocity is sublinearly increases. If you increase the electric field, if you increase the more and more electric field, so chance of collisions increases, so the drift velocity somewhat decreases. So that's why we can say sublinearly increases. So in this case actually what will be the mobility here actually? The mobility is proportional to under root of E. Under root of E actually, right? This is about medium applied electric field. And third case actually, what is the third case actually? The third case is nothing but if you apply the high applied electric field. High applied electric field. What happened? The drift velocity is constant. The drift velocity is constant, or we can also say saturate. Saturate means it will reach maximum value. Okay. Here why the drift velocity is constant actually? Because the increasing drift velocity due to applied electric field is compensated by the decreasing drift velocity due to mobility. See, one side the drift velocity increases due to applied electric field. Another hand, the drift velocity decreases due to collisions, right? See, this is increasing, decreasing, increasing, decreasing. What will be the resultant actually? Constant. That's why the drift velocity is constant or saturated. Okay, if you apply high electric field actually. Now in this case, what will be the relation between mobility and applied electric field? The mu proportional to 1 by E. Mu proportional to 1 by E, right? Now, I'm going to draw the plot actually. That is drift velocity versus applied electric field, right? See, if you apply the small applied electric field actually, that is E less than 10 power 3, what will be the drift velocity actually? The drift velocity is linearly increases, right? If you apply the medium applied electric field, that is 10 power 3 and 10 power 4 actually, what about the drift velocity actually? The drift velocity is sublinearly increases, right? This is the sublinearity. And if you apply the high electric field, what will be the drift velocity actually? Constant. This is the drift velocity versus applied electric field plot. Next, I will also plot the mobility versus applied electric field graph. So in case of small applied electric field actually, what will be the mobility here? Constant. The mu is constant, right? If you apply the medium applied electric field actually, what about the mobility here actually? The mobility is sublinearly increases, that is mu proportional to e power minus 1 by 2, right? If you apply the high electric field, actually what will be the mobility here? The mobility is linearly decreases. That is mu proportional to -1. Linearly decreases. This is the mobility versus applied electric field graph. Right. This is the effect of electric field on interrupt velocity. Copy.